Good evening, everyone, and welcome to Online AP Physics. I'm Mrs. Eliezer, and we are picking up with Chapter 15, Simple Harmonic Motion, in our first day's adventure with COVID-19 and school closures. Welcome to everyone in the world who has no idea who I am and hasn't been riding the roller coaster with me for the past 2 years. I'm going to summarize everything that we were supposed to finish up last week, but we're interrupted with national news and a school closure. Start with any problem with a restoring force, specifically a restoring force that's proportional to the displacement. Hooke's law is one such example of a restoring force that's proportional to the displacement, F equals negative kx, in the horizontal direction. We've seen another force that's proportional to displacement in the case of the gravitational field inside a planet. If you're the Magic School Bus Dig to China, if you're underground with some of the mass over your head, you remember we found that the gravitational field was linear as a function of r, and that means if you have a gravitational field g, you have a gravitational force of mg. Look how that little m appears. Note that both of them have one major thing in common. It's not the geometry. Hooke's law is one-dimensional. Gravitational field is radial. It's the negative sign, restoring force. If you pull a spring left, it pulls you right. If you are above the center of mass of the planet, it pulls you down. If you're below, it pulls you up. These are restoring forces. And if we set them up as differential equations, we'll notice that the solution should have the same setup. Again, reviewing our steps to setting up a differential equation. Analyze the net force. If you're lucky, there's precisely one. Otherwise, look for nasty boundary value conditions to get your initial conditions right. There's your force, ma, in the appropriate direction. Hooke's law, we're going to have an acceleration in the horizontal direction, the direction of your spring. In the case of gravity inside a planet, we're talking radial acceleration, a vector. If we're very unlucky, it's x, y, z. However, if we're lucky, we can just get away with a unit vector r in the radial direction, only go the opposite way. Second step in writing a differential equation, get the a by itself. This is always the same, divide by m, people. It gets old real fast. The third step is to write this as a differential equation. The AP exam is expecting you to say d squared x over dt squared. That's fine too. I happen to like this notation because it says I don't have fractions, I don't have division, I don't have multiplication, I am a second derivative. What is acceleration the second derivative of? It's the second derivative of x. Again, we can see the same thing. It's the second derivative of x and y and z in that order. That is, it's the second derivative of r. Now, big picture, review from everything we've seen before. This says in calculus, what is a function whose second derivative is equal to itself, only negative, and with a mess of constants out front? The answer is simple harmonic motion. Every differential equation we've seen in calculus-based physics has followed this pattern. If it's a first-order differential equation, it's going to be exponential growth or decay, as seen in populations for growth, and Newton's law of cooling, EMF, and back voltage for exponential decay. You see what function has its first derivative proportional to itself, only with some junk out front. If the junk out front involves a sign change, that's going to be decay rather than growth. The second order differential equation we saw by dint of enthusiastic testing has the exact same solution set of the first. Take two derivatives. The only difference is that instead of bringing down the rate once in the first derivative, you bring down the rate twice, once in the first derivative, once in the second derivative, and for that reason, we write the group of constants out front as the square of some useful number rather than the original up here. Both biological networks and electrical networks in AC circuits with inductors and capacitors and resistors follow this pattern. You have to look at the initial conditions in the equilibrium case for A, controlling the exponential growth part of the term, b controlling the exponential decay part of the term, and c the constant out front here, which is setting our equilibrium value here, or final asymptote. What function is equal to its own derivative, only negative? Well, in real numbers, sine and cosine. Yeah, this should say cosine. Sorry about that. It says cosine on the updated note sheet. As demonstrated very aptly by the senior stooge who came in for QuarkNet help and stayed for calculus, take two derivatives of a sine, you get itself only negative, and, as per your chain rule, some junk out front. The A, or as we said in class, the B, is the amplitude. The omega is the angular frequency, which is closely related to its angular speed in radians per second. And you sometimes have to monkey with the phase angle, or the phase constant, or the phase shift to make sure you're starting at the correct part of the period relative to your initial conditions. Short answer, we're dafka not expecting to go through 0, 0 in this. If we go through the point 0a, that's a cosine. If it's any one of those other two, and by my count, we have 2 down, 358 to go, we're going to need a phase shift. Checking in, F, or nu as you called it in chemistry, is the frequency. That is omega over 2 pi. Let me be clear on this. Omega is the square root of whatever constants you have out front. I'm going to say that again, nice and slowly, because it's the secret to any simple harmonic motion problem anywhere, ever. Omega is the square root of all the constants out front. Look at our restoring forces. Omega, for Hooke's law, is what? Pause and write it down. Okay, now try omega for the gravitational fields problem. Pause, write it down, put a box around it, plus play when you're ready to check your answers. You got it? Omega, the angular frequency for a mass on a spring undergoing simple harmonic motion, is the square root of k over m. That means the period is 2 pi divided by the square root of k over m. Take that reciprocal, flip it now, you'll get 2 pi times the square root of m over k. That's the formula that you see on your AP review sheet for AP Physics 1 and AP Physics 2, and this is how they got it. AP Physics 1, AP Physics 2, AP Physics C, probably IB for all I know. Hi everybody who's quarantined for COVID-19. Hope you're enjoying the physics lesson. That's where the period comes from. Now let's try this again for the magic school bus as they try to dig to China under the surface of the Earth. Omega should be the square root of gm over capital R cubed, where m is the mass of the planet they're digging through, and capital R is its radius. That means that the period of oscillation for the magic school bus or anything else that's under the surface of a planet trying to dig through is 2 pi times the square root of r cubed over gm. The negative is how we know it's simple harmonic motion instead of a growth and decay network. All the constants out front take a square root and they go straight into the angular frequency. Now, play around with external conditions. We've got omega. If you take a spring, if you take a mass m, load it up, stretch the string to some initial length away from equilibrium, and let go, notice that in this case it was down rather than up, you're going to see it vibrate from whatever position away from equilibrium you started it. In our case, a negative cosine, omega, that's the square root of k over mt, with no phase shift. Take the first derivative of that function. See what happens to the square root of k over m and a, and see what the maximum velocity is going to be in one dimension of that spring. I know it looked vertical on the picture, but there aren't any good quality animations for horizontal. So only one force, no mg, just kx. What sort of maximum velocity are you going to get? Look at the leading coefficient of that sine term. Take the second derivative, look at the acceleration, and compare to your earlier equation. If you can get your early equation, your original function, negative cosine, with whatever k over m is out front and a sign change, then you have proved your point, QED. Pause, work out the problem yourself. Take a look at your answers. If you get the second derivative working out, you know you've done it right. What's more, your leading coefficient will be the maximum acceleration, and you can plug in time equals 0 to note that when t is 0, the initial velocity jolly well ought to be 0 because it was at rest when you let it go, and you can find the time at which it achieves its maximum acceleration. Pause, press play when you're ready to do the next problem. Frankly, if you've done Hooke's law, the next problem isn't so bad. It just has a few more letters under the square root. Here's your function. You've got a nice differential equation here. You know what the omega is. It's the square root of everything in between the negative sign and the original function. You can write it as x if you don't like r. Find your x. Again, you're starting at x equals 0, so that's going to be pretty clear whether it's sine or cosine. Whether it's positive sign or negative sign, now take a look at your new boundary value condition. Instead of being given an initial position, which, let me be clear on this, without an initial amplitude, this is going to be real hard. You're given an initial velocity. Well, leave A for now. Take the first derivative, the coefficient of your sine or cosine function, whatever it is, chain rule and all, it's going to be equal to your initial velocity. You can therefore get A in terms of your initial velocity without having to result to conservation of energy yet. Conservation of energy will be 2 lectures from now. Happy differentiating!